Okay, right, we're going to talk about how to make phenylamine, right, this stuff here. Right, by the way, the phenyl group is a benzene ring. It's like an alkyl group, so it would be C6H5, okay? Why is it H5? Well, because you've stuck something onto it, yeah, like, you know, NH2 there. So that carbon hasn't got a hydrogen attached to it. So that's the phenyl group C6H5, that's there. Okay. So how would you make this? Well, let's think about how would we make, say if we wanted to make ethylamine. Now the way we've done that, and you do it briefly in year 12, do it in year 13 as well in more detail, is if you'd use a haloalkane, and you would react it with ammonia, which is a nucleophile, and you get nucleophilic substitution, NH2, and you get Br minus and H plus. So that'd be nucleophilic substitution. Now, can we do the same with, could we do the same with, say, bromobenzene? Could we just react that with NH3 with ammonia? And the answer, of course, is no, because what kind of reactions does benzene undergo? It undergoes electrophilic reaction with electrophiles. And this, of course, is a nucleophile, so that's not going to work. So the way in which it's made is this then. You get, first of all, you get benzene. And that is nitrated to make NO2. And then that, so you form your nitrogen carbon bond here, and you replace those oxygens with hydrogens. So you've got phenylamine. So the question is, what kind of reaction is this one here? What kind of reaction is it? Well, we've removed oxygens and we have added hydrogens. So that is organic chemistry. Removing oxygens or adding hydrogens, as we've seen before, is a reduction. And what reducing agent are we going to use for that? Now, the reducing agents we've come across in organic chemistry before, well, we've come across sodium borohydride, haven't we? That won't work though, because this only reacts, this is actually, it's a hydride ion, and that is a nucleophile. It's not going to work here. Okay, so the reagent we have to use is one that's not used in any other, for anything else. It's specific to this reaction, and the reduction is carried out by tin in conc HCl. Right, this is tin, and tin is not a catalyst here. It's that tin is actually the reducing agent. So I'm going to draw some half equations here, but then I'm going to show you how the exam board want you to represent it. So tin is a reducing agent because it tends to form SN2 plus ions. So it gives away those electrons. What's happening with so I'll draw the benzene, and I'm going to draw the C6H5, the phenyl. I'll draw it as that. C6. Okay, so that's your benzene ring, the phenyl group, yeah, NO2, and that's going to go to C6H5NH2, NH2. So let's see how do we balance half equations? Right. First of all, we balance for oxygens with waters. So we've got 2 oxygens here, yeah, and we haven't got any oxygens on the other side. So I'd have to put 2 H2O. And then we'd have to balance for H plus ions. Well, I've got 6 more hydrogens on the right hand side than on the left, so I'd want 6 H plus. And then I'd balance for charges, so I'd need 6 electrons. Okay, so that is that. They're the 2 half equations, but the way you represent it is you don't essentially. So you're adding H plus and E minus to the nitrobenzene. You represent that as H in a square bracket. Okay, it means that means a hydrogen atom, which is coming. Okay, and the hydrogen atom is coming from the HCl, H plus in the HCl, and the electron is coming from the zinc, from the tin. Sorry, that's what's happening there. So the way the example would want you to write this equation is C6H5NO2 plus 6 hydrogens in a bracket goes to C6H5NH2 and 2H2O. That would be the equation that you want there. So I'd remember that, yeah, and don't forget that the catalyst, it's not the catalyst, sorry, the reagent is tin in conc HCl. And so the tin isn't a catalyst, it's a reducing agent there. And that's the only mention tin gets in the whole of the A-level syllabus, I think. Okay, so that's how we make phenylamine. And if you have a look in the amines section, you'll see that phenylamine doesn't behave as a normal amine. It's not a very typical amine because you have a lone pair on the nitrogen there. And normally, so for example, if you've got methylamine, that's quite a good base. Why is it a good base? It's good at accepting H pluses because what's it got? It's got a lone pair on the nitrogen. This is a poor base. It's a very poor base because the lone pair is not available to pick up H pluses because it's partially delocalized over the benzene ring. Okay, and incidentally, that makes the benzene ring more susceptible to electrophilic substitution because you've got a higher electron density on the benzene ring because this lone pair is also in there, partially delocalized in there.